Good day everyone. Today we're going to discuss about the thermodynamics heat engine. So there's some applications and processes regarding to the how heat engine works and some types that you could gain in listening and watching in this video. So let's talk about first the definition of a heat engine. So it states here that the heat engine is any device that changes thermal energy into mechanical work, such as steam engine or an automobile engine. Invented by Nicolas Leonard Sadi Carnot. He was a French physicist who did experiments on several things. That's the reason the heat engine is also named the Carnot engine. So it is very useful. It is very useful in many ways, like in the vehicles we drive every day, refrigerators that we stored our foods, coolers, and the computers we use today, and some other mechanical equipment that we are using today. And it was very helpful for us as a human to make things done easily and work faster than we expect. So his main aim was to convert the heat energy into a useful work which benefits the society. So we are really benefited to this kind of um, inventions or discoveries and the figure 1 of our video. So this is the basic behind any heat is that the mechanical energy. It can be obtained from a thermal energy only when heat is allowed to flow from a high temperature to a low temperature. In the process, some of the heat can then be transformed to a mechanical work. So as a diagram schematically in the figure 1. So it useful heat engines run into a repeating cycle as we can see. So that is the system returns repeatedly to its starting point and thus can run continuously. We have here two types of heat engine, which is the internal combustion engine or the what we call IC engine. So from the word itself, which means that this IC engine, which combustion takes place within the engine. The chemical energy of the fuel is converted to a thermal energy and the thermal energy is converted to mechanical energy. So these examples, which are the gasoline engine, diesel engine, Honkel engine, open cycle gas turbine. Another type of heat engine is the external heat engine, which explains that in which combustion takes place outside the engines. So the heat produced during the external combustion is used for inducing useful mechanical motion in the cylinder of the engine. So we have here the example of AC engine, which are the steam engine, steam turbine, and closed cycle gas. Here the working process of two-stroke heat engine. So we have the reciprocating type, turbine, or the boiler and the condenser. So in reciprocating type, as we can see in the illustration, the heated steam passes through the intake valve and expands against a piston, forcing it to move. As the piston returns to its original position, it forces the gases out the exhaust valve which is open. So a steam turbine is very simple except the reciprocating piston. So that is the letter B. The turbine, which is the boiler and the condenser, is involved. Turbine is very similar except that the reciprocating piston is replaced by a rotating turbine that resembles our paddle wheel and many sets of blades. Unlike to this turbine, which is very simple, and our electricity today is generated using these steam turbines. The material that is heated and cooled, steam in this case, is called the working substance. In an old-time engine, the high temperature is obtained by burning coal, oil, or other fuel to heat the steam. Steam engine and internal combustion engine figure or illustration, we can see that the reciprocating engine and the turbine engine are reciprocating type, and turbine is very useful for us today. We can here we have the four-stroke cycle internal combustion engine. So we have here the intake, compression, ignition, and the exhaust power. Now talk about first the intake stroke. So this is what happening or the process within the internal combustion engine in the first stroke. So the stroke of the piston begins at the top dead center or the TDC and ends at the bottom dead center, which is the BDC. In this stroke, the intake valve must be in the open position while the piston pulls an air-fuel mixture into the cylinder by producing the vacuum pressure into the cylinder through its downward motion. So that is what happening to the process inside or within the intake stroke. So the second one is the compression stroke. Here in the compression stroke, this stroke begins at the PDC, unlike to the intake stroke which starts first with the TDC, which is the top or just at the end of the suction stroke. Also, it ends at the TDC. So, in this stroke, the piston compresses the air-fuel mixture in the preparation for the type of stroke, which is the ignition. During the power of stroke, both the intake and exhaust valves are closed during this stage. So both valves are closed. So in this working stroke, it starts the second revolution of the four-stroke cycle. So at this point, the crankshaft has completed a full 360-degree revolution. So while the piston is at the TDC or at the end of the compression stroke process, the compressed air fuel mixture is ignited by the spark plug or firing gasoline engine or the heat generated by the high compression, which is the diesel engine. So forcefully, this stroke produces the mechanical work from the engine to turn the crankshaft, and it's now exhaust stroke works. So this exhaust stroke or the last stroke in the cycle of the internal combustion engine happens the piston once again returns from the BDC to TDC. So while the exhaust valve is open, the action expels the spent air fuel mixture through the exhaust valve, and it happens or it this process runs repeatedly or continuously as this internal combustion engine works. So we are going to talk about also the efficiency of the so as we can see here in the equation, E, of any heat engine can be defined as the ratio of work it does or the W to the heat input at the high temperature. So E sensible definition since work, or the W is the output, or the for us QH is what you put in and pay for in burned fuel. So since energy is conserved, the heat input, or the QH, must equal to the work done plus the heat that flows out at the low temperature, or the QL. You can see we have here a four um, type or kind of formula for the efficiency, for computing the efficiency of the heat engine. So let's now go to the exercises, or the example exercises of the heat engine. Exercise number 1 is certain heat engine does 10 kg of work and 8.50 kg of heat transfer occurs to the environment in a cyclical process. What was the heat transfer into this engine? So we have here given of W, which is the 10 kg. So exercise number 1. A certain heat engine does 10 kg of work and 8.50 kg of heat transfer occurs to the environment in a cyclical process. What was the heat transfer to this engine? So we have here a given, which is the work 10 kg, QC, which is the 8.50 kg, and QH is what we are going to find. So we have here formula of substitute it formula, and then we have a 18.5 kg heat transfer to the engine. Ship does 2 times 10 raised to 8 joule of work with an efficiency of 5%. How much heat transfer occurs to the environment? So using the shown in this video, just substitute all the given in the problem. 0.0500 as our efficiency, 2.0 times 10 raised to 8 joule for our work, then substitute, and then you can get the 3.80 times 10 raised to 9 joule, which is the amount of heat transfer occurs to the environment. So exercises problem number 3. A coal-fired power station is a huge heat engine. It uses heat to transfer energy from burning coal to do work to turn turbines, which are used then to generate electricity in a single day. A large coal power station transfers 2.50 times 10 raised to 14 joule by heat from burning coal and transferring 1.48 10 raised to 14 joule by heat into the environment. So, what is the work done by the power station? We have here given of QH, which is 2.50 times 10 raised to 14 joule. QC is equals to the 1.48 times 10 raised to 14 joule. And then the work is what we're going to find. So we have here the solution. Just substitute all the given in this problem, and then you can get 1.2 times 10 raised to 14 joule. Next problem, or the next exercise problem. Car efficiency. So in an automobile engine was an efficiency of 20% and produces an average of 23,000 joules of mechanical work per second during operation. So here are the question. For the letter A, how much heat input is required? For the letter B, how much heat is discharged as waste heat from this engine per second. So in the letter A, we have a given of 23,000 joules if of work. The efficiency is equals to 20% or 0.20, and the QH is what we are going to find out. So using the equation, the formula, just substitute all the given, and then you can find, and you'll get 1.15 times 10 raised to 5 joule, or 115 kJ. So in the letter B, continuation of the QH, which is the 115 kJ, and then just substitute all the given, and then you'll get 92 kJ. And that